Okay, so we're going to transition over to Sebastian Englehardt. Sebastian has a bachelor's degree in biology from the University of Kaiserslautern, Germany, and a master's degree in biomimetic from the Carinthia University of Applied Sciences, Austria. Sebastian did his doctorate in integrated biosciences at the University of Akron in Ohio, where he explored strategies for water reclamation from waste streams using aquaporin-based membranes in forward osmosis. Sebastian is currently based in Hamburg, Germany, where he works as a territory manager for the American company Ecolab in the water, hygiene, and energy industry. Welcome, Sebastian.
Thanks everyone for tuning in, and greetings from Hamburg, Germany. So I want to talk today about a research project that I worked on during my PhD at the University of Akron in Ohio that focused on the development of a lightweight filtration system to reduce the volume of urine during long duration cave exploration, which most of you know is sort of a problem on long-term caving trips. So I'd like to start my presentation with that image that I really like, because this is the Lake Castrovalva, I believe, in Lechegia Cave, if I pronounced that correctly. And what I like about that image is that you can see really that a cave is really like a pristine ecosystem, and only like a handful of people or like a few people have access to that. And that is why it's really important that these ecosystems, and especially those microbial communities living in these ecosystems, have to be preserved. So caving trips in these environments are therefore sometimes a threat if external contaminants, like for instance human excretion products such as urine, get introduced in these environments. And urine specifically is a threat. And this becomes clear when we take a look at the following table, which shows the composition of synthetic urine in that case. So this is just an estimation. And what is important here to consider is that if we take a look at the main nitrogenous contaminant or compound, we have like 25 grams per liter of urea in 1 liter of urine, which is quite a lot. And if urine is going to be left in the cave, then you basically leave a lot of excess nitrogen in this environment, which is usually a nitrogen limited environment. So that being said, it is usually important that urine is going to be removed out of the cave after the exploration. Also, what is important to know is that 95% of urine is actually water. So when I heard about this problem, I was thinking, is there maybe not like a possibility that we can kind of recycle that majority of the water from the urine, and with that sort of like reduce the amount of the contaminants that have to be carried out of the cave after the exploration. So I am personally not a caver, but I had one cave experience where Hazel took me on a trip, which was really fun, in the Carlsbad Caverns National Park. Maybe some of you guys have been there. This is called the White Giant. So it was like a 4-hour trip. And on our way there, I really realized that this whole caving thing is really challenging. If you kind of have to kind of like crawl to all of these little tunnels. So it was my first time, and made me realize that it must be challenging to carry so much equipment down there. If you, for instance, have like a multiple day caving tour. And so that being said, made it really clear to me that like removing all of this urine usually is not feasible. And also for any kind of innovative technologies, we would have to consider that any filtration system has to be very small and lightweight, so it can easily be integrated in the gear that the cavers usually bring down into the cave. So just want to give a few numbers and like some examples. Most of you probably are aware of that, but cave explorations can usually last up to 8 days or even longer. And if we consider that a well-hydrated adult excretes about, if we average it, let's say that 150 milliliters of urine per day, you can see how much amount of additional weight and volume actually accumulates over like a week caving trip. So for that reason, it is not practical removing all of this urine. And I think the current practice is that the urine is usually be left at specific campsites, and which obviously is not the perfect solution. So that again kind of brings us to the point where we may want to discuss, is there any lightweight portable filtration system that is possible that we can create, that we can reduce that urine volume and less has to be carried out. So before I want to talk about the work that we did, I just want to kind of talk about a couple of strategies that have been tried in the field. The first was the so-called infamous bucket, I got told, which was basically the idea that like a bucket was used to collect all of the urine with the hope that over time the water from the urine just evaporates, which apparently did not work because of the high humidity in the cave. So that led to the result was that none of the water actually evaporated, but the result was just like kind of a muddy mixture that accumulated in that bucket over time, which was actually worse than the original or initial urine. Then I think activated charcoal was another trial, which would have worked great for certain salts and charged molecules, but charcoal is not really working if you have molecules that do not carry a charge, because they're simply not attracted to the activated charcoal particles. So urea has no charge, unfortunately. That's why it usually just goes straight through these filters. Another strategy that was tried was reverse osmosis, or RO. Reverse osmosis is basically like a pressure-driven filtration process. So what you have is you have like a semi-permeable membrane, which usually is permeable to water, but rejects like larger contaminants. And then you pretty much press with like a lot of pressure against this membrane and force that water through. And ideally that membrane is selective enough that it kind of holds all of these contaminants, like in our case, urea, back. Problem with this is that you need a lot of energy. I think in the cave, people were using this for like kind of sort of like a hand pump. But the problem is that those membranes are very sensitive to fouling, because if you apply a lot of pressure, you pretty much push those contaminants into the membrane, which causes the fouling. So those membranes clog pretty easily. And then when you push then with a really high pressure into the system, then there's a risk that the system pretty much falls apart, which I heard happened, and which led to the spilling of urine all over the cave. So this was also not a strategy that was very promising. So what alternatives do we have? And there is one technology I'd like to focus on for the next couple of minutes that is called forward osmosis, or FO, which is pretty much the opposite of RO. What forward osmosis is using is a natural osmotic gradient. So we have the same principle. We have we call this a feed solution. In our example, this will be our urine that we want to filtrate. And this feed solution is also separated from a so-called draw solution with a semi-permeable membrane. So this membrane, again, lets water pass through and ideally rejects all of the contaminants. And on the other side, we have something called a draw solution, which is basically any solution that has like a higher osmolarity than our feed solution. And that leads to the fact that water from our feed solution actually gets pulled into the higher concentrated solution, so that this solution gets diluted. So if we would start that process, and this is animated here, over time, water flows over the membrane. That means that the feed is getting concentrated, and the volume obviously is being reduced as the water gets pulled out of the solution into the draw. And this process runs until we reach osmotic equilibrium on both sides of the membrane. And at this point, there is no water flux anymore, so the system is pretty much in balance. And this is where we would usually stop the process. And then is the question, what are we doing then with our final solutions? So let's focus on the feed solution, or in our case, the urine first. Depending on what feed solution it is, in our case, if it would be urine, you would just carry that smaller amount of volume out of the cave and just dump it somewhere outside. If it's something hazardous, you would either incinerate it, or it might also be a feed solution that you can recycle with certain technologies. Then the draw solution, we also have different types of draw solutions. I just want to name a couple of examples. The most basic one is sodium chloride, just salt. For instance, if you want to clean ocean water or so, let's say you have oil spill in ocean water and you want to use FO for that. Pretty much you would just absorb all of the water in a concentrated salt solution, and then you just dump this clean salt water solution back into the ocean. There are also more sophisticated draw solutions. For instance, ammonium bicarbonate is one, which can be evaporated on really low temperature. I think ammonium bicarbonate boils off at around 50 degrees Celsius. So this stepwise process is then more energy efficient as if you would have evaporated the water off right away from the urine. So this is also a strategy. And now what is important for us, this was our idea, if we can just use like a sugar solution, like a glucose solution. So our end product would just be like a drinkable isotonic sugar solution that the cavers could just drink during the caving trip. So that was the initial idea. So our goal would be reduce our urine volume, concentrate the urine, carry that amount, that smaller amount of urine out of the cave, and then the rest of the water that got recycled can be consumed in form of a drinkable sugar solution. So the good news is that forward osmosis has been tested. It's a new technology still, but it has been tested, for instance, in the ISS. And it is really enables like portable and lightweight systems. And also because osmotic pressures are driving the process, this is an energy neutral process. So that is perfect for being used actually in a cave environment. So what are the challenges and the goals? So we have two main challenges. First of all, we would like to have really high water recovery, because the more water we can recycle from that feed stream or that urine, the less we have to carry out. And the more water, obviously, we also have to dilute our sugar solution. Problem is here that urine has a very high osmolarity. That means we also need a very high concentrated draw solution in order to create that osmotic difference. So we actually have water being pulled over the membrane. The other problem is that urea is a very small and uncharged molecule. That means that most membranes might have troubles rejecting it. Here you can, for instance, see the comparison of the molecular length of urea on a water molecule. So you see that urea is not that much bigger. So it's a very small molecule. So therefore, we would need an FO membrane, which has a very high water permeability, but is also very selective towards urea and rejects most of the urea. So by that being said, we got to ask ourselves now, how can we solve this problem? And we kind of always sometimes like to follow like a more biomimetic approach and ask, how would nature solve this problem? So are there any solutions in natural systems? And for instance, if we take a look at the kidney, and more specifically take a look at the collecting duct, which is the end part of our system, where the urine actually gets concentrated because water is being absorbed back into the bloodstream. When we take a look at this structure, we will see that there are specific proteins that facilitate that water transport. And those proteins are called aquaporins. They sit like they're transmembrane proteins that sit in between the lumen of this collecting tubule or duct and our bloodstream. So they pretty much shoot water molecules through and really kind of increase the speed of water transport. And what is also interesting about these structures is that they're very selective. Like there's some aquaporins that can only let water pass through because they have a very narrow constriction that doesn't allow any other molecules to pass. And luckily, also E. coli produces this protein. So this protein can actually be produced and be purified out of E. coli culture and then be embedded into artificial membranes. And there's one company in Denmark we collaborated with. It's the company AQUAPORIN-BASED from Copenhagen. And they are producing the first commercially available aquaporin-based membrane, or also ABM. It's the abbreviation for that. And the good thing is that these membranes also exist in a very compact and small hollow fiber configuration. So like very small modules, as we will see on the next slide. And so this is actually a very promising candidate to use coming up with like a filtration system that can be used or integrated in the Caver's gear. So here we start with our experiment. So we ordered a couple of membranes and we set up our system. So we had our feed solution, or urine in this case. We placed this on a balance in order to monitor the volume reduction over time. And then we have like a pump. So we pump, like we cycle that feed stream through the membrane over and over again against the draw solution, which in our case could be salt or sugar. I mean, for the proof of concept, we can use anything. It just has to be higher concentrated than the feed. And so we do this over a course of a couple of minutes, and then until the feed is being reduced by, let's say, 80% or whatever our goal is, and there's no water transfer anymore. So ideally now we would take samples from feed and draw and analyze if anything of the urea went through the membrane. So this was the first part of our study, to determine the rejection of the membrane. So ideally our end result would look like this. I don't know if you can see this. Ideally, none of the feed contaminants or urea would go through, so we just have like a really up concentrated feed stream and a really clean draw solution. That would be the ideal scenario. The not so ideal scenario would be that if some of these feed contaminants actually pass through the membrane. I don't know if you can see those little green dots here, that just should represent that some of these actually pass the membrane. So this is just like just to clarify what that actually means, rejection. So this would be a perfect rejection. Here we would have a certain percentage that went through the membrane. So here is now a video of actually the basic setup and the actual experiment. So this is kind of speeded up by 80 times or so. So I'll start this right quick, and there you will see now actually how on the left side the urine really gets concentrated over time, gets really dark and almost brown. And you can also see, and that's the good news, that on the right side here, I think it was a salt or sugar solution, I don't remember exactly, but you see that this really stays clean. So none of like the more colorful contaminants at least do not go through the membrane, which is first of all a good sign. And let's just one more time, and then I switch to the next slide when we see a before and after comparison. So let's look here. So this is our initial urine, and this is our final urine. So you see a really big difference, and you also see that the water from the urine got absorbed into the draw solution, diluted this, so we have like really a high volume here. So well, this is good, but first of all, we have to do the analysis and see actually did urea go through or not, because we can obviously not see this with our eye. And this is our data. So we ran 3 experimental campaigns. First of all, we were testing, we tested 3 different draw solutions just to see if that makes a difference. So we tested glucose. This is part A. We did choose sodium chloride, and we also analyzed magnesium chloride. And you can see here, this is the rejection. So everything which is close to 100 obviously is perfect. So the higher those bars are, the better. And what we see here on this axis is the water recovery. So we kind of took samples after 25% of the water was pulled into the draw solution, after 50 and after 75. So that's why we just wanted to compare if that also makes a difference, and it does. You can see that the more water you recover, the worse the rejection gets, which was kind of expected, because obviously the higher you concentrate your urine, the more is also the likelihood that more of the urine actually passes the membrane, because you just have more in solution in relationship to the volume. And so what for us is important is we should take a look only at these yellow columns, because our goal is to reduce as much water as possible, or as much volume as possible from the urine. So that being said, we can see that this rejection here is high, but probably not high enough to allow for a drinkable draw solution, because we have about 80% rejection. When I see this correctly here, maybe a little bit more, maybe a little bit less if we take a look at the sugar experiments. And that means that still quite some amount of nitrogen actually goes through the membrane. And we're not really sure about the health effects of a prolonged consumption of a draw solution that actually has nitrogen in it. So this is definitely maybe not a safe practice. So at this point, we had to discard this idea for now and move to something else. And the idea was then eventually we can just use salt and not having a drinkable draw solution anymore, but maybe we can just like use this as a more inert end product of our process that could eventually be left in the cave. And it probably is better to leave like a salt solution, a clean salt solution in those dumping sites and the cave camps instead of actually urine, because here we have less nitrogen that gets introduced to the system. But obviously the effects of the salt on the ecosystem also would have to be studied. But this is maybe we thought this might be an alternative approach. So for that reason, we just stick to the salt. We just said that we use salt for the prototype development, just for the proof of concept, and worry about the effects on the ecosystem later once we have built that prototype. So this was sort of our initial version of our prototype. So we used actually a smaller membrane module here that was designed for being used by one caver. You could argue later on that maybe it makes sense if we have a bigger membrane and the whole caving crew is sharing the same equipment, but we just tried to build as small as possible. So that system is pretty basic. So you will have two hydration bladders, one for your urine. So you fill the urine in here, then you have your draw solution back here. And what you do is just use gravity in order to facilitate that flow of those liquids. So you just lift those bags up, and both fluids will flow through the membrane into their outlet reservoirs. Like your urine will then flow into here, draw solution will flow into here, and by flowing through that membrane, a part of the water should have been absorbed into the draw. Then you pretty much turn the whole system around 180 degrees and repeat the process to let this flow back. And you do this over and over again until you see that the volumes don't change anymore and the majority of the water actually got transferred into the draw solution. And this was the data of our lab experiments. So here you see the volume. So we started with 1 liter of urine, and we started with 500 mils, a little bit more of draw solution, sodium chloride in that case. And you can see that those numbers are every flow through the membrane module. So after every number, we turned the module and repeated the process, and we did this for about 5 times, because after 5 times you see that here the volume doesn't change anymore that significantly. So at this point we probably reached osmotic equilibrium, meaning that we do not repeat that process. Usually stop this right here. And you can see that from 1 liter we pretty much reduced the feed, so the urine, to under 250 mils. And proportionally, obviously, the draw solution increased as the water got transferred over here. So in these lab experiments, we achieved a water recovery of 80%, which is pretty good. Total nitrogen rejection was 70%, which was quite okay, but could be better, of course. But the membranes did not allow better rejection, unfortunately. And also what is maybe interesting to mention is that the time to process 1 liter of urine took about 15 till 20 minutes. So this is also a broad process that can be done during the cave exploration. So it's not that it takes hours to do that. So that's pretty good. So now after this, we actually had another idea to add to the system, but this was just like a workaround method just to add and to test. We were thinking, as we have as an end product a very clean salt solution here, we could eventually try to like boil off that water if we just use like a regular outdoor stove that has been used in cave exploration expeditions anyways. Of course, you could argue now, well, why don't you boil off the water from the urine initially? And that's true. Maybe there are some mechanical solutions that will allow for like a system that you can safely evaporate the water from the urine straight. But we thought we might just try this because we have here a cleaner solution. So maybe this would be more acceptable for most cavers if they say, well, yeah, okay, I can use my stove in order to boil off that water. So that would allow that we can actually reduce that draw solution volume back to the initial 500 mils, and then we pour water in there. So then we do the process again, absorb the water into the from the feed into the draw solution, and then we boil it off again. And we did some lab experiments because obviously we would had to make sure that none of the nitrogen that went through the membrane that did not get rejected is getting lost in the cave atmosphere. And we did some experiments in the lab, and we measured the concentration before and after the evaporation process, and the concentrations pretty much matched really perfectly. So none of the nitrogen actually got out of the solution. So only the water evaporated, which was good. So if we use this principle, we did this process.
Sebastian, you've got 5 minutes.
5 minutes, that is fine. I'll be able to manage to finish in this time. Yeah, so we were thinking about coming up with an example just to see what would be the weights to be brought into the cave and out of the cave. So let's assume we would have an expedition of 8 days, and we do have 1.5 liters urine per caver per day. That would accumulate to 12 liters of urine per caver in that week. So that's like 12 kilograms. So if every caver would need to use this equipment, we would have one set that would be 600 grams that would have to be brought into the cave. We would have sodium chloride, about 100 grams, 120. And obviously we need a couple of more gas cans because of the evaporation, which is like a total volume or weight of 1.12 kilograms. And then the weight that would have to be brought out of the cave, assuming we can leave this FO system in the cave for later usage, we would have the main component would be the concentrated urine. If we assume 80%, we're going to reduce, that would leave 2.5 K to be carried out of the cave after the expedition. The draw solute, so after we boiled off all of the water, the draw solute would be a little bit heavier because of the nitrogen that accumulates in it, which didn't get rejected. So this is just an estimation. And obviously the empty gas cans after we boiled off the water would also add 200 grams to the system. So approximately 3 kilograms is what you would have to bring out of the cave. This was actually tested by Katie Bender, my lab colleague. She actually optimized that system. So she came up with like a more smaller size prototype and tested this in the cave. Unfortunately, the whole evaporation process didn't really work out that well because of the high humidity in the cave. So the amount of gas we needed in the lab environment was definitely not enough to do this in a cave. We actually, I think it was about double or even more that has to be used. So that being said, this whole evaporation strategy was just for us an idea to test out, but probably not the way to go. So what would be the next steps or alternative approaches? I got to mention that, I mean, I've been working on this for a couple of years and also used different generations of that aquaporin membrane. And I observed that that membrane actually got better over time. And so there's still some hope that while those membranes get optimized and getting further improved, that actually we will reach a rejection of total nitrogen that is sufficient so that we can follow this approach of having a drinkable sugar solution eventually at some point. We could also investigate what impacts it would have on the ecosystem if we just leave salts in there. This is maybe a study that can be done. And also we should determine what is the critical limit of total nitrogen that's actually drinkable. So let's say we approach 90% rejection of total nitrogen. Would that allow us for a 1 week expedition to drink that sugar solution with some remnants of nitrogen, or is that a health issue? So that's something that we should take a look at. So that brings us to the conclusion, which tells us that urea rejection is actually quite challenging. So it wasn't easy. That is primarily due to the small size and uncharted nature of the molecule. We introduced a lightweight prototype of an FO system and achieved 80% water recovery, while we could reject 70% total nitrogen. And we also seen that this draw solution recovery over evaporation is not really the best strategy to go for. But we still have some hope that those membranes get better over time, and maybe in a couple of years, this might be a technology that could actually work. So then I have some people to acknowledge. I think I'm almost done in time. So first of all, my PhD committee, obviously, especially Hazel, helped me a lot and guided me through that research. I'd like to thank Rod Herrick's Aaron Lynch from the Carlsbad Cavern National Park and US National Park Service for funding this research. Also the company in AQUAPORIN A&S and Dr. Jörg Vogel from Denmark, Copenhagen, they helped me a lot, provided the membranes and also assisted me with technical questions. Also like to acknowledge my former corporate sponsor in the IB program, Ross Environmental Services, and Joe Sherman, as well as all the integrated bioscience students and UA staff that helped me during my time at Akron University. So that is, well, right in time.